Hello and welcome to week 4. So this week, I just want to let you know that the midterm exam is coming up. That begins Tuesday of week 5. So that's June 26th is Tuesday. You can take it on any one of these days only. This is the window. So you can take it Tuesday, June 26th, Wednesday, June 27th, Thursday, June 28th. Now the campus is closed Fridays and Saturdays always during the summer. So the next time you could take it would be Monday, July 2nd, or Tuesday, July 3rd. Now that's your window. That's 1 week from the date it's assigned to the date it's due. So please plan accordingly. The review is up in Canvas. In there, you will see the due dates as well as the content being covered. So I won't go over that here in this video. Keep this video short, and I can trust that you can read through that. So please do as soon as possible so you know what to expect and when to come in. Read it very, very, very carefully. There is you have 2 hours to take the exam, and they collect exams 15 minutes before they close. So if they close at 5:45, for example, I'm not saying that's the time they do close, but if they close at 5:45, for example, then they would collect tests at 5:30, which means that if you want to give yourself the full 2 hours, you need to start by 3:30, which means you should probably get there by about 3 or 3:15 at the very latest in that situation in order to be able to give yourself the full 2 hours time. By the time you check in and everything, if it's busy, you just never know what to expect. So plan accordingly as you do that, and let me know if you have any questions. So week 4 due dates. This is the cutoff for the midterm, meaning it will cover exam weeks 1 through 4. We have a discussion board due Wednesday, homework due Sunday. No quiz this week. This week you'll be looking at the discussion board will be market competition as a game, so using the idea of probability and expected value, and the content for this week, I'm sorry, is actually the focus will be more on the introduction to hypothesis testing and some key ideas there. So I wanted to go ahead and wrap up the discussion board. This problem is a little tricky because there are many ways to find a match. Now, matching birthday. So you have, so many people in a room, and the question are you going to hear people say, yeah, we have a common birthday? What's the likelihood of that? Well, here's the reality. There are many ways in which that could happen. So let's consider this to be the sample space. It's the set of all possible outcomes. And we have 28 people in the room. So I shouldn't say either, but it's possible that there are no matches at all, right? So, 32 people. So 32 people all have 32 different birthdays. Not unlikely, right? You probably expect that. There are 365 days in a year, ish. 365 and a quarter, I think, if you take the average from year to year. So having 32 different birthdays is not all that, maybe not all that unlikely. The other possibility is you have one pair of common birthdays, right? So that means that there is, out of those 32 people, 30 of them have different birthdays than one another, but then the other two have the same birthday as one another. You have one pair of common birthdays. So that could be person 1 and person 32, or person 1 and person 2, person 1, person 3, person 1, person 4, blah, 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 and then person 2, person 3, person 2, person 4. So there's just many ways in which that event alone can happen. Well, what about the possibility that you do have common birthdays, but there are two pairs of common birthdays? Or there are, one triple of common birthdays. So maybe people 1 through 29 have no birthday in common, but people 29 through 32 have the same birthday in common. So that's another way to find a match. We didn't say it had to be exactly two people who shared one birthday. We said it just what's the likelihood that there's a common birthday. They can be two triples of common birthdays. So maybe people 1 through 3 have June 28th, and maybe people 29 through 32 have April 18th as their birthday. So this goes on and on and on. Now you can have people, 4 people who all have the same birthday, and 28 others have different birthdays. And then the most extreme possibility is that 32 people all have the same birthday. Probably fairly unlikely given the number of days in a year. So the way we want to look at this, rather than to think about all of these events, right? Because what we want to do is we want to find the probability of this and all of these events, and we really just want to add up all of these probabilities that correspond to this 100% rectangle. So the only people who we don't want are these people who have 32 different birthdays for this situation. So rather than to figure out all these individual events and their probabilities and then add them all up, what we can do is we can sort of think about this as, well, this whole box is 100%, And if we just take away the stuff that we don't want, the event that we don't want to happen, which is that we have 32 different birthdays, and that gives us the likelihood of having at least one match of birthdays in the room. So we approach it from that perspective. Take away the stuff that you don't want. So imagine you have a big stack of papers, and it's a foot, a stack of papers that measures a foot in height, and there are three pink pieces of paper in there. Well, you're not going to go through that 1 foot stack sheet by sheet and wait until you hit a pink one and then pull the pink one out. You're going to look at it from the side. Right? You're just going to kind of delve in there, and you're going to pull that sheet of paper out, and you're going to drop the stack back down, and you're not going to go page by page. So this this uh, this situation here represents us having to kind of go page by page. Here, we just kind of take away the ones that we don't want, and or pull out the ones that we do want, and then we're good to go. So really what we need to compute then is the probability that there are 32 different birthdays. So that's the same as saying is that person one has a birthday, person two has a different birthday than person one, person three has a different birthday than persons one and two, person four has a different birthday than persons 1 through 3. And because we want all of these events to happen, this is joint probability. We're going to multiply these probabilities together, keeping in mind that they're independent, because the fact that your birthday is on June 22nd does not change or affect the likelihood of my birthday being or not being on June 22nd. Regardless of what your birthday is, the likelihood that my birthday is June 22nd is 0, because my birthday is not on June 22nd. So we continue in this fashion up until the 32nd person, and that's the probability that person 32 has a different birthday than people 1 through 31. Okay, well, the way this works is person 1 has any birthday, that's 365 divided by 365. That's the probability of that, right? Likelihood that you have any birthday is 100%. Everybody has a birthday. Probability that person 2 has a different birthday than person 1 means that they can only have a birthday on 364 of the 365 days, because person 1 has already taken one of those days. So we're looking at the event that person 2 has any one of the other remaining birthdays. And person 3 has a different birthday than person 1 and person 2, which means that they can only select from the 363 remaining days. Now, I know we're not selecting, but this is as if we were selecting, right? We're basically isolating these events down and saying, what would it mean for person 3 to have a different birthday than person 1 and 2? And we continue on in this fashion. Now notice that this stops at 334, and 365 minus 334 is 31, not 32. That's because we are starting counting at 365. If you count 32 places down from there, include this as 1, 2, 3, 4, 5, 6, 7. By the time you hit 32, you're on the 334 days remaining. Okay, so that's what we can do. Now we notice that this is just 365 to the 32nd in the denominator, and this is 365 times 364 times 3. That kind of looks like a factorial notation, except that I don't want to keep multiplying down all the way to 1. So what I'll do is take 365 factorial and divide out the 333 times 332 times 31, because this one accounts for that. This one divides those out. So this is just a more optimal way to do it in a computer. Otherwise, you can multiply 32 factors all together, and you get 0.247. So the likelihood that there is no common match at all is only about 25% chance, which means the probability of at least one match means the 1 minus the probability that there aren't any matches, which is 1 minus 0.247, which is 0.753, meaning there is a 75.3% chance there is at least one common birthday in a group of 32 people. So that doesn't necessarily mean there will be a match, but it is more likely than not. All right, that's it for this intro video. Hope you have a great week, and let me know if you have any questions.